All right, so um, we're going to talk about the three different versions of, um, or kind of viewpoints of a dot product. So in my head, there's really like, if you have two vectors A and then B, you know, then you can do A dot B, right? And there's kind of three ways to think about this. So the dot product A dot B is equal to the magnitude of A times the magnitude of B times the sine of the angle between them, right? And then there's also kind of the other viewpoint. So this is one. Two is basically, you've got your x and y axis, right? And let's say you have a vector here and another vector here. And then what you can do is you can drop a, perpendicular here, right? And now whatever this component is, that times this component gives you the dot product. So, um, there's a couple ways to write it out, but I'm just going to leave it there for now. And then the third way is A dot B is equal to A1 B1 plus uh, A2 B2, right? And they say, these are all supposed to be the same thing, but I didn't really understand why until today. So these two, I think, make sense why these are the same, right? So let's say, this is A or this is B, and also there's tons of other videos and stuff explaining why these two are the same, and in books and stuff. So I think these two you'll be fine finding, but basically it's just, if you say this is B, right, and this is a right triangle, then oh, I think it's cosine. Um, Whatever. But so yeah, if this is theta right here, then you have the magnitude of B times times the cosine of the angle between them gives you this component, right? So then this component times the whole length of A that's what this is. So these two are simple to go back and forth between, and again, that's everywhere. But so the question I was having was between these two. I didn't really understand why, but um, so one thing I noticed, like this one seems like this is about the components, right? So in my head, this is a component of A, so it's A times whatever the basis vector is, plus A2 times whatever the basis vector is. So it seemed like, if you change your basis vectors, then you get different components here. So then, so it seems like this would change with your basis vector, and this shouldn't change with the basis vector. I didn't even like draw basis vectors in here, right? So, like the length of A and the length of B and the angle between them don't have anything to do with the basis vector. So I was like, well, I don't understand why these are the same thing. But so I I think the answer is because that as long as you have an orthonormal basis, then this will not change even if you change your basis. So what I mean by that is, so let's say you have a vector space, this is j hat, and then this is I hat, right? If you all of a sudden rotate your basis vectors so it's like I hat is here and j hat is here, and they both have length 1 and they're perpendicular, these are orthonormal, ortho, orthonormal, these two, it looks like I'm drawing basis vector, but then these components will change, but their dot product will stay the same. So like for example, what normally when you'd write this, you would assume that your basis vectors are I hat and j hat. So let's do let's call them. When I was doing this earlier, it was like, let's call this one L and this one M. All right, so these are our new basis vectors. They're unit vectors, so I'm gonna draw little hats on them. So now we're gonna have so A B is going to be like A1 prime, B1 prime plus A2 prime, B2 prime. And I was like, so these components are different. So, I mean, these numbers are different and these numbers are different, but somehow, I mean, the geometry remains, so it seems like they should be the same. And it turns out that they are. And so that's why these work is because, so if you have your normal basis vector here and here, then what you can do is rotate them. So now you have this one as one and then the perpendicular as another. And now all you need is A is just one component, and then B has two components. So it's this component, but it also has the other one. So, but the other one is multiplied by zero. So this still works, right? So let me draw it a little bit bigger. So what's the best way to? I'm gonna do it like this. I think people, yeah. Okay, I'm just gonna draw here, right? So I, J, and then like you have this vector, that's A, and this is B, A, and then what do we get? Something like this, right? And then and so then here, so this component, so like B in the A direction times A gives you your dot product. But what I'm saying here is if we now rotate and we have L here and M here, so now A's components are going to be, so A now is going to be equal to just the magnitude of A, comma 0, right? Because A does not go in the M direction at all. And then B is going to be, whatever it was. It's like the projection of B onto A, right? And then it's going to be whatever this is. Let's just call it X. So now when we dot these two, we get A times projection of B onto A plus 0 times X, which is a 0, which is why I said we don't care about it because, you have something, something in this direction times 0 in that direction for A. So we get A times projection of B. Whoops, misspelled. B onto A, which is exactly what these two are. And it worked in this component way. And it's just because you can rotate this orthonormal basis. And we can prove that the orthonormal basis rotation, it we can prove that it works. I didn't use actual numbers here, so we didn't prove it, but I can do that in the next video. But just to reiterate, this one and this one are the same because when you rotate your vector or you rotate your basis vectors, your answer doesn't change, and you can see it really works when you make one of these as your basis vector and the other one perpendicular because now we just have the component in one direction and the other component